Okay, so this brings us to the end of interconnection networks, and what I wanted to talk about was deadlock. So let's assume that you have 3 nodes, labeled 1, 2, and 3 here. It's on a 1D torus that is unidirectional. So links only flow in the clockwise direction here. Now, all of a sudden, you have node 1 wants to send to node 3, node 2 wants to send to node 1, and node 3 wants to send to 2. And we're going to look at a wormhole routed network. So in the wormhole routed network, you start to send the header words, and the tail has potentially not even been injected into the network at this point. Let's say they all start exactly at the same time. So 1's going to start sending to 3, 2's going to start sending to 1, 3's going to start sending to 2, and what you'll notice is each set of these has one overlapping link with the previous one. So there's going to be some contention on that link. So very quickly, you can see that if we were to launch these 3 messages exactly at the same time, and the message length was long, none of them would actually get to the receivers. 1 would use this link, or 1 sending to 3 would use this link, 2 sending to 1 would use this link, 3 sending to 2 would use this wraparound link, but then all of a sudden, they would try to acquire the next link, but it's already been reserved. But they can't give up the link because they've already acquired the link, so all of a sudden you have a deadlock. So these networks get pretty tricky. And one way that we go about trying to see if our routing protocol is deadlock free or actually can deadlock is we start to do something called waits for analysis or waits for and holds analysis. And waits for and holds analysis, the basic idea is, so this is looking at our example that we saw before where we have 3 routers. What's happening here is we're injecting into A, and this A is acquiring this link or this FIFO here, and then it needs to acquire the next one. So let's draw this as a diagram. So A holds TQ2. So A holds TQ2, this one here, this inbound queue here. And when we draw waits for and hold analysis diagrams, when we're waiting on something, we draw an edge from the thing that is doing the actor to the resource that we're waiting on. And the holds actually goes in the opposite direction. So if A holds TQ2 here, we actually draw the edge the other direction. So all of a sudden, A is holding TQ2, and it's waiting to acquire TQ3, this one here, because it needs to transit that link to deliver it into 3. But at the same time, B has acquired TQ3, so it's holding that, and it's waiting for TQ1. But C currently is holding TQ1 and is waiting on TQ2. So this is how we do deadlock analysis from a proof perspective. We actually will write these dependency graphs, or waits for and holds graphs. And if you find a cycle in your protocol can have a deadlock. And you need to come up with some way to cut a link here or cut an edge in this graph, or you need to completely redesign your protocol. But this is the sort of canonical way that you can do this. And if you start to look at different routing protocols, some of them can possibly deadlock, and some of them you can prove statically that all possible waits for and hold graphs you can come up with will never have cycles. So as I think I mentioned last time, if you look at dimension order routing, with wormhole routing, all possible inputs and outputs on that, you're never actually going to have a deadlock. You'll never come up with a cycle in the graph. And the reason for this is you only ever acquire X routers And then Y routers will say if you have the dimension that you acquire X and then you acquire Y. But you're never going to have effectively something that is holding Y trying to acquire something on the X-axis. So you're never going to have a cycle in that waits for and hold analysis graph. I just briefly wanted to sum up here that deadlock is actually not an enemy. You can try to use deadlock to your benefit or just live with deadlock. Just because your protocol has deadlock does not mean you can't try to recover from it. So what I mean by this is deadlock avoidance can be very expensive. So trying to draw all possible graphs here, you should think about where your deadlocks happen in your systems and plan them out and make sure they don't happen often. But some of the things you need to do to try to cut edges here might be too restrictive. So for instance, dimension order routing where you only route in the X dimension and then the Y dimension could be very expensive relative to an adaptive routing scheme where you try to route around congestion in your network. So this deadlock avoidance, you'll design the protocol to never deadlock, but this can be quite expensive. So alternative, and this is something you should not necessarily be afraid of, but you have to be careful of this, is that you find the deadlock and then you try to recover from it. So what I mean by this is on an on-chip network or a multi-chip network, you can actually have a deadlock occur, notice that a deadlock occurred, and either try to roll back the state and somehow jitter the state so the deadlock won't happen a second time, or many times these deadlocks happen because you're dependent on one particular buffer in the system and two people trying to acquire that buffer. So you can try to virtualize that buffer, effectively saving the state of that buffer into memory and adding more state. So a lot of these protocols, if you were to add more FIFO entries into the system, it would actually break the deadlock. So sort of going back into this picture here, if all of a sudden if I added another, let's say, FIFO here that the inbound traffic went into and then this other traffic tried to bypass it, it would actually cut one of these edges and all of a sudden you would not be having a deadlock. So you can think about trying to have a deadlock recovery mechanism, and that is an example of it. So a good example of this is actually in the raw microprocessor from MIT, where you can actually have deadlocks occur on the on-chip network. It's dimension order routed, but you can still have message dependent deadlocks. So what I mean by that is while the network itself is not going to deadlock, the traffic flows you have on top of that, for instance, your memory coherence protocol on top of that, could potentially deadlock. So how do you recover from that? Well, you can actually have a counter, a timer, which goes off when you determine that the network has not moved for 1,000 cycles. So all of a sudden you're running along and no traffic moves on your network. Well, it's a pretty good indicator that you have a deadlock condition because something should be flowing. There should be some forward progress guarantees. And if you notice that, an interrupt will go off. So this timer will go off saying nothing has moved on my network for 1,000 cycles. This is probably a deadlock. So that you can take an interrupt and then software can go look at all the state in the network and introduce more buffering into the network. So effectively through software, try to virtualize a particular FIFO entry and that can break the deadlock. So there are ways to recover from deadlocks. If your network is, for instance, used for your message passing network, you can just use memory to go do that. So actually, on the raw processor, our memory coherence protocol, we used deadlock avoidance, and then our message passing protocol or message passing networks use deadlock recovery. Later on in Tylera, actually, we have something, depending on which memory network, we have mixtures of these two. And you might say that sounds scary, but if you walk through the proofs and you're very careful about it, and you're guaranteed that you don't need any more resources to go break the deadlock, you may be okay. But yeah, it's to some extent, it's playing with fire. You gotta be a little careful with these sorts of solutions when you're trying to play with deadlock recovery. But if you're guaranteed that you're not gonna need more resources, you can just resolve it right then. And so the reason you would want to use deadlock recovery is it does not restrict your protocol. And by doing that, you can have the common case of your protocol be very, very fast. And you could make it so that the deadlock almost never happens, or never, in practical concerns, ever happens. And then when the deadlock does happen, oh, you take a little bit of a performance bump or performance hit there because you have to virtualize it in software, but the probability of it happening is so low.